Welcome to the second season of the Kern Competence podcast, a podcast about all things Kern and precision. Today, for episode 4, I'm once again joined by my co-host Simon, but also by Vreni Höck. Welcome.
Hi, welcome Marvin.
Hi.
Simon, do you maybe want to introduce Vreni?
Yeah, so I would say a little bit short notice. So we asked Verena to join us for the meeting for the podcast today.
When we say short notice, while I was setting up the microphones, I suggested, hey, we should get Vreni on board, and you were on board, and she was just walking by, and I just shouted, Vreni, come in!
Yeah. So honestly, you said, I have a third pair of microphones with us, and therefore let's have a third candidate. So Verena is our product manager, and from a marketing perspective, the person responsible for our new Kern Fortis and the whole introduction. And Vreni, perhaps you tell a little bit more about yourself.
Yeah, I think I'm with Kern since 2017.
That's quite long already.
Oh yeah, almost like 7.5 years. Yeah, that's quite long. I started with an internship half a year. And then, now I'm a product manager, so
Okay.
Quite a good way. Yeah.
So, Verena studied with Kern, and she finished her school and did multiple jobs in marketing and whatsoever, and then found her passion in marketing, which was a big positive surprise for me at that time, and now making her way through the organization and a career, and today being responsible together with the technical guys for our NPIs.
Yeah, and that's only with 24 years old, so.
You're originally also from this region in Bavaria.
Yeah, I'm from, it's called Schöffau. I think there are more cows than people, so quite a small town. It's only
I think this applies to most towns in this region.
Yeah, that's true. But I'm from the region.
Okay. We've spoken about you a couple of times in the preparation for the Fortis podcasts. So, for example, Simon told us you're responsible for the name.
Yeah, I am.
Yes.
So any complaints directly to Verena, then not to me.
You will be at EMO, so people can come up to you and complain.
Yeah,
or
of course.
show their appreciation for a strong name. You're there the whole week?
I'm there the whole week, yeah.
Very cool. Okay, for today's podcast, and I mean, seeing the time we are uploading this, the morning EMO starts, we're going to unveil everything about this machine. So today we really want to dig into the technical specifications. Something we've teasered in the previous episodes is that Fortis is a big machine. And maybe before we start digging into the real deep details, Simon, could you tell us a little bit, like if you had to compare HD and Fortis in a couple of sentences, what are the similarities and where do you see Fortis as something more?
Yeah, that's a super difficult question, and the reason is the point of view. Looking through Kern eyes, of course, the machine is a totally different kind of an animal. It looks kind of similar from the outside, so design and I would say the overall architecture of the machine, but going into technology, there's a lot of enhancements necessary to reach the absolute final goal, which is what we established with the Kern Micro HD. So the ease of mind, the ease of use, so really focusing on process, because the machine is extremely stable, intelligent, and reliable in many ways, fast and precise, very dynamic, wear-free, all those things that we love about Micro HD and our customers love. This is now transformed into a new dimension, which is Fortis. And this is so hard to do. If you ask the engineers we have running around here, Christian Meyer, for example, I think you
previous podcast, yes.
The guy looks like 65-year-old, and I think he's beginning of the 30s. No, I'm just kidding, he's looking good, but actually it's been stressful years to accomplish what we say, getting the quality of a Micro HD in a new dimension. So really big work pieces, and we're going to talk about the dimensions and so on. And it was really it was the hardest technical challenge Kern ever had. And we're super happy to say today that we accomplished that mission, and you will tell later on if we really reach that goal, and you will be super honest as always. But from my perspective, super happy to be where we are.
Yeah. I think you could probably put the difference into one sentence, and that's basically it's about twice in every dimension at a similar accuracy. Yeah, okay. Let's talk about the hard technical specifications. We've told everybody it's much larger, so let's talk about travel. Vreni?
Yeah.
Vreni has to look it up. So the problem is not just like 400 by 500 by 400. It's a little bit of a crooked number.
Yeah. Maybe to explain the crooked numbers before Vreni actually tells us about the crooked numbers, what our development typically does is they try to limit the length of an axis, because the longer an axis get, the more you get accuracy deviations. You can, for example, see this on most CMMs, that they state an uncertainty. For example, on a size Prismo, this is like 0.5 microns. And then you always have a value which is called L divided by a large number, for example, L divided by 400. And this means the length you're measuring over, so for example, 400 millimeters, then your actual error would be, or your uncertainty would be 0.4 plus 400 divided by 400, so another micron. Now, our development typically does FEM simulation before they start on the machine, devising a way to maximize workpiece size while keeping the kinematic loop as short as possible. Okay, let's get into the details. Vreni, the travel.
The travel is in the 3-axis system. It's 780. Was soll ich denn mal? By. Okay, 780 by 420 by 450.
So that's X, Y, and Z
That's
direction.
X, Y, and Z, yeah.
Okay. That is huge. That is, I think, more than twice of what the HD actually offers.
Yeah.
Huge travel range. This obviously comes with a much larger maximum workpiece size. Simon, what have we designed for maximum workpiece size on this machine?
So we always make a difference, of course, between 3 and 5 axes, and what you will see right away is that the overall architecture, and I think that's important, also the 3 axes are positioned very similar to like the Micro HD. So we didn't go back to Gantry or Bottle or whatsoever. It's going to be the superior design we saw in the last couple of years, decade, that is so beneficial for us, having the axis outside of the milling chamber, away from all dust, abrasives and whatsoever. And in 3 axis we're going to have 565 by 400 by 350 in Z, and in 5 axis you could say it's a 565 times 350 in Z, so a circle of 565 times 350, which is really big. And at that point, if you want to put a workpiece, and you did actually, if you want to put a workpiece of that size on the machine, you very quickly come to a point where the maximum load is near.
Yeah. I also have to say, while I was preparing the sample parts, I think my most spoken out complaint was I am too weak for this machine. Because on the HD it's so cool. You can just like grab your workpiece, grab your vise, and just lift it in, and there's no danger of like hurting your back or anything. And with Fortis, every workpiece I've done for this sample preparation, I was unable to lift. So you have to get a crane, you have to lift it in. It's a much more preparation than we are used to on this one. Maximum workpiece weight is also quite interesting on this machine, because as Simon said, the size is actually quite huge for a Kern machine. So obviously we had to bump the workpiece weight.
Yeah, it's actually 6 times bigger than on the HD. It's 300 kilograms.
Which translates to roughly a little bit more than 600 pounds.
Yeah.
That is massive parts.
It is, yeah.
One of the sample parts we did in like when it was the raw stock nearly approached that weight. I think we were at 280 kilograms when lifting it in. And I mean, we were quite lucky. One of our colleagues, Christoph Steidmeier, who has a lot of experience with big machines, he was doing that. I was just like, we can't lift that. This is way too heavy. How can we lift this part? But he knew everything, how to grab around part at that weight.
He's a strong guy.
Yeah, he could probably. I mean, I think when we were drilling the holes for like lifting it with a bolt, he moved that part around on the pallet himself. I was just like, Christoph, it's over 200 kilograms. You can't move that. And he's just like moving it. Okay, large workpieces and large travels also require a powerful spindle. And I mean, we called it Fortis, which means strong. So there's going to be a new spindle in this machine.
Yeah, so the one thing was clear at the very beginning is looking at, and I don't want to call it the field of competition, but you see you have 50 upwards, mostly 63 as an HSK. So of course we also gonna have an HSK 63 spindle in. It's gonna be a core cooled spindle, so a CSC compact shaft cooled, like you know from Micro HD and HD Plus, where we have an HSK 40. CSC brings a lot of advantages in terms of temperature stability and extension and so on. So we have this masterpiece, and we have to say so. I think there's no one else using that spindle today besides us. Using, yes, but offering it in the field where we are in, and quite impressive results. So the machine and the spindle is really powerful. The tools are very heavy. So I saw maximum tool weight is 10 kilograms.
Yeah.
Compared to Micro HD today, I think we don't have a lot of tools around that extend 1 kilogram.
Yeah, not at all. I think I was so the machine is set up at the very end of our building. We obviously did this because we've been milling on it for over a year now, that not every customer who comes in sees we are doing something new. We wanted it to be a surprise, of course. But our tool loading station is at the very beginning of the building, because that's where we are with our customers. So whenever I had to set a tool, I had to grab like 2 or 3 HSK 63 holders, walk to that setup station and walk back. And okay, I'm probably just too weak for this machine, but if you have 3 large HSK 63 holders in your arm, your biceps is gonna hurt by the time you arrive at the machine. So that was it's enormous. So Simon, you already told us about maximum weight for the tools. But Vreni, could you tell us a little bit more about the technical data? What's the rotational speed of the spindle?
Yeah, so the max RPM is 24,000 for the HSK 33, which would be interesting.
63?
63,
Oh,
yes.
sorry, 63.
Yeah,
which
that's actually massive for an HSK 63 spindle. The majority on the market are running at 18,000 RPM.
Yeah, that's right.
And there is a couple of 30,000 RPM HSK 63 spindles. And we actually just inquired about them, and the manufacturers told us they are horrible. They are only made for removing aluminum. They have no precision whatsoever. Don't get that spindle. And well, if the manufacturer tells you don't get that spindle from the beginning on, we knew, okay, it needs to be high RPM, and 24,000 is quite quick.
Yeah, would be interesting. What is it in horsepower? Do we know that?
Yeah, sure, the KKN knows 47 brake horsepower.
Yeah, 47 horsepower, and that's
a small car.
that's 35,000 watts, so 35 kilowatts of spindle power. If we compare this, an HD has around 15,000, so that's massive.
Mm-hmm.
Yeah. What's the maximum torque?
The maximum torque is 90
Newton meters.
Yeah.
That is, I have to say, insane. I know one of the requirements when we set out for like defining the spindle was basically drilling with like an insert drill in stainless steel, and the requirement was we want to do more than 35 millimeters. And I mean, that is humongous. That's like, if you see the drill for that, it's just like, it's out of your mind. If you see this on a Kern. Exactly. I think our like up to now for the HD, our tools we have like in stock, the largest drill is like 11 millimeters. We never used something bigger because just like on those high speed spindles, you're missing the torque for larger drills. And now with Fortis, you're more like limited by there are no larger drills for that spindle interface. So that's really cool.
I think it's also fair to say that, especially the development of the spindle, getting the experience in that HSK 63 took a lot Fischer, so it's going to be Fischer spin from Switzerland again, was extremely fruitful, but also it was kind of a development for both sides
Yeah.
to get the requirements right and to really meet the requirements that we had at that time, and they did a good job.
I mean, you always have to remember that when we use a spindle, it's not just that we take a spindle from the shelf, slap it into the machine, and then our work is done. So just like we did on the HD, the compact shaft cooling, which is, I think, from a thermal perspective, the best thing you can do for a spindle, the standard is to just pump temperature-controlled oil through that compact shaft cooling. And we are the only company in the world that uses a load adaptive system for this. And this changes everything. So yeah, of course you can find other machines, because Fischer is selling to a lot of machine tool companies that have that same CSC spindle in the machine, also on the HD. But ours is outperforming everyone by a large margin, multiple factors, because we just do temperature management the way you should do it and not just the simple solution for this. And obviously, for that new spindle, we had to adapt that, and it's not just changing the parameters. It doesn't work as easy. Yeah. Something I absolutely love about this machine is the tool changer. And Vreni, I've seen you putting tools into the machine multiple times.
Yeah.
Can you maybe tell our listeners?
Yeah, I did.
Yeah. Can you maybe tell our listeners a little bit about the tool changer? Just like, what does it feel like going up to the machine?
Okay, so it's huge. So if you stand in front of the machine, or especially in front of the tool changer, there is a little step, so you can reach the top of the tool changer.
And I have to jump in on that. So in Bavaria, the most important thing you have on your house or farm or whatever is your tractor. And the quality of the tractor and what you bought, what you have, is actually determined by how many steps are there until you reach the cockpit. And you have won your we call it a Chlorheisler, mean a small houser. So you have a very small farm, you can't afford more. And if you have 2 steps, that's kind of pretty cool already. 3 is crazy good. So what I said from the beginning on is we need to have a step somewhere at the machine. It doesn't have to be 3 steps up or something like that, but at least 1. So, and we got it. I love it.
Yeah, I love it too, because I wouldn't reach the top if it wasn't there.
I could tell our dear listeners, when I was doing the sample parts, the machine I was working on, they took a couple of things apart in that tool changer. So there was no step, and there was no sheet metal on the inside, but I needed to reach the top shelf. And it's so strong, I started climbing the tool changer to reach the top shelf. But yeah, as you said, Simon, 2 steps is cool, and we actually have 2 steps. There is 1 step leading up to the tool cabinet, and it's a similar style tool cabinet to the HD. So we don't have a loading station where you spend hours waiting for the tool changer to put the tools away. It's once again a cabinet style. You can open the door. There's a button directly next to the door that opens the door, and then you have basically an identical tool changer to the HD.
Yeah, it's same, but bigger.
Yeah, exactly. Full accessibility again.
Yeah.
And then inside that tool changer, you have another step to reach the top shelf.
Yeah.
And both Vreni and I aren't very tall, so if we can reach it, I think everybody can reach the top shelf with that step.
And by the way, I think it's worth having another 2 sentences about that, because in the first prototype that we've made on Fortis, really the operator panel, and you have the same kind of very good overlook on the machining chamber. You can see the workpiece like in the Micro HD. Of course, the window is a little bit bigger, so it looks even a little bit more accessible. But the problem is that the workpiece changer the tool changer, sorry, not the workpiece changer, the tool changer is kind of broad, so it's kind of big. So from where you stand, it's true for the Micro HD too, you cannot look inside the tool changer. So what I did after the first design approvals with customers, for example, or with selected partners, so okay, we need to have some kind of visual accessibility of that thing. So now there's a big window there where you can, from your operation panel, can look into the tool changer, see if, of course, everything's right, grabbing the right tool and whatsoever. So things you want to do from time to time, if if you're prototyping or start running a certain process. And so this gives you a lot, I would say also again ease of mind and accessibility, which is really great. And you don't want to grab the wrong tool or whatever. So therefore, that was a great idea. They gave me a hard time actually because they pull out the chip conveyor, so you can run directly from the panel to the tool changer, which I think is not necessary, but
Yeah, you haven't worked on that machine.
yeah.
So on the first prototype, you have to walk around the chip conveyor to get to the tool magazine. And let me tell you, if you run around that 20 times a day, you want to shoot yourself. Especially, but I mean, this is why we do prototypes and why we test them for over a year before we are actually launching the machine. Because on that first tool changer design, we put the button to open the tool changer directly next to the user panel. And if you forgot to press it and you walked around the chip conveyor, you stood in front of the tool cabinet, but you couldn't open it. And then you kind of had like two options. The first one was to walk back around. And I think I've told before on this podcast, I broke my ankle joint this winter. It's the left ankle joint. It's quite good now, but not completely stable. The version I always did was like plant that bad ankle joint on the very slippery angled chip conveyor and lean around the machine while holding the handles of the tool changer to press that button. So this was basically a Berufsgenossenschaftsunfall waiting to happen. Now, this is the prototype, which I don't think is ever going to see a customer. On the final version, not only does the chip conveyor extend a little bit further out, so you can actually walk through, and that step extends over it again. But also the button is directly next to the door handle. So if you forgot to press it, well, you just press it there.
Yeah.
That's a really nice change, yeah.
Yeah.
And there are, I think, thousands of things we were not going to cover today, but this was impressive to see along the project. How to move from a first design approach, and we said, we did that in micro HD, let's do it again, and you see, it's not going to work.
Yeah.
And it's the same thing, for example, how we change tools in micro HD today is different to
Tomahawk.
the Tomahawk. Finally, we had some sales reps here that they were always talking about an L speed or a Tomahawk, and can we do this, can we do that? Yeah, we finally have the Tomahawk everybody wanted, and it's impressive how fast it is.
I'm not quite sure on the number. Do one of you guys know the maximum tool amount we can put into at HSK 63?
Yeah, for HSK 63, we have 41 places for the big tools for 390 millimeters.
Maximum length, yes.
Yeah, and 108 places for the smaller ones. So
149 tools in total?
yeah.
Yeah. And in HSK 40, so I think we didn't mention that before. Of course, there's an HSK 40 version, which is, I think, highly relevant because many of our customers have this need the high RPM, have small tools, but have big workpieces. In the meanwhile, I think this is something that we're super happy of, that this didn't change. So this trend is continuing to say parts get bigger, parts get higher precision. Integration is also assemblies you did before is now one single workpiece that you have to work on a machine. So HSK 40 will be relevant. So we have the HSK 40 CSC2. And how many places do we have in the tool cabinet?
For the big tools, we will have 129 places for maximum length 250 millimeters and 220 places for the smaller tools.
So that's 350 tools in total?
Yeah.
That is insane.
No?
Yeah, and I have to say 250 millimeters maximum length is also really nice, because so far I think this was one of the most spoken out complaints about the HD, where you get 150 millimeters plus 5. People were always like, we need longer tools, and well, now you get longer tools. Yeah, that is one massive tool changer, and I'm especially happy for HSK 40 that we kept that open cabinet design, because can you imagine loading 350 tools through a loading station one by one?
Or on a chain.
Chain. Yeah. That's really cool. We also have, of course, it's like a finished product, so we can maybe talk a little bit about coolant. We once again have a coolant recycling device next to the machine. It's made again with our partner Knoll. It's massive.
Yeah, it is massive.
Yeah. I think the current version takes 1,600 liters of coolant or oil.
1,700 liters.
1,700, yes. That is massive. It has a couple of filtration stages. So I think there's, once again, a paper band filter, but there's also cartridge filters.
I would say everything that we have at Micro HD right now. So we see the need and what we learned over the last couple of years. And of course, also looking into, and by the way, we're talking about massive, this is enormous. If guys from Grope or Herman,
Yeah, okay, they are not laughing.
They will not stop laughing and say, oh, okay, wow, 1,700 liters, okay. But for us, it's massive. And so everything that we use for the Micro HD today will be possible with Fortis. Of course, in another dimension, but there's plenty of technical solutions, and even going to a centrifuge in the future, something like that. All that is possible. Especially also the temperature management of our coolant liquid, respectively. The flood coolant is, of course, on the same level as with Micro HD. Doesn't make any sense to let that slip.
Yeah, I mean, the amount is also needed from a technical perspective, because this machine not only has a higher through output of coolant, obviously there's more flood coolant going through it, and there's once again through spindle coolant, again with 80 bars, which I think is 1,600 psi. Do we have a psi number on that?
No,
Okay.
I don't have that here.
It's 80 bars. Then of course we have like a table flood coolant supply to wash down chips, and we have bellow flooding, and we have window flooding, just like everything you would expect from a big machine that is designed to make chips. And overall, I think the number Christian told me was 250 liters per minute is the maximum that gets poured. You really have to say poured into the work area. And if you want to have good temperature management, you just need a larger reservoir. If you put about that much, that amount of through
70
it.
gallons, roughly, a little bit more.
Yeah.
So, wow.
Yeah. But it's been working really nicely. I would have expected, because coolant typically, because that's an aggregate most machine tool companies do not build themselves, I would have expected that one to be like a little bit of an issue, but it has been working flawlessly, and the coolant is always super clean. That's really nice.
From the beginning on, I think this is worth to mention. So we did a lot of pre-work, but this thing worked from the beginning on.
Yeah. Knoll did a good job there, and I think also our PLC department in the integration. I think we spoke about most important technical specifications. Did we miss anything?
No.
So, one absolute funny fact is that we still don't know by 100% the weight of the machine. We will know when we ship it. That is the thing. From overall, the machine looks very similar to the Micro HD. It's going to be a little bit broader, of course. As we said, the tool changer is more or less the same setup. We have this magazine. We have an L-Speed or a Tomahawk in there to allow very quick tool changes. As you said, from the inside, of course, there have been a lot of learning. So we started with, like in Micro HD, with the milling chamber being painted or spray painted at the beginning for protection. Forget about it. I think that's the first part you did. It was just like sandblasted on the inside. Okay, we say, we have to change that now. It's stainless steel, of course, from the top to the bottom. These are things a little bit embarrassing, but
I mean, they're mostly embarrassing to me, because I think this is the third machine I've ruined visually at Kern.
it's just really okay.
Yeah, just visual ruination, So I burned down one. I once completely wrecked with sandblasting the Hermle standing in our apprentice department, and they've been milling on Fortis on the prototype for over a year, doing customer workshops, test cuts, their own verification. The machine basically looked brand new, and then I was on that machine for 3 days. It was a tight schedule for the first sample part. And I just decided like, hey, there's 100% of spindle load, so let's use 100% of spindle load. And I just sandblasted that machine, and now it looks like a 20-year-old machine. Where I'm really happy that in the future everything is like stainless steel covered and the paint is not gonna come off. So if on like any of the like Instagram clips we're gonna load up, you see a dirty ass machine, that's my fault. Totally, 100%.
So I think Verena had a hard time actually getting good shots while filming.
Yeah.
For Fortis because of the fact that you couldn't show the actual milling chamber of the machine, but just the part itself and blur out the rest. But the machine we show on the fair is going to be a flawless stainless steel. Everything's good. This just to mention. We also have 2.5 years, 3 years now of really learning also big machining, and it is different. So also when you ask what's the difference between HD and Fortis, of course we're using the same principle. Microgap hydrostatic, integrated linear drives, different dimension. So I said that the last time, I think our the 3x aluminium body we have in a micro HD is 360 kilograms with everything in. It's 360 kilogram. I think the y-axis is a ton on a Fortis. So this is just one part of it, and of course all the principle works, but the microgap hydrostatic looks a little bit different. We will not reveal why and how, because patents pending, or respectively the applications ongoing for that, but also in weight countermeasure and whatsoever, we needed different kind of approaches to achieve highest possible stability, wear freeness, and so on. So if you look at, and you will see from what Verena did with the team in the last couple of weeks and months, showing the inside of the machine, this looks different than a micro HD. I think that's fair to say.
Yeah. We've prepared a couple of applications, so I've spoken about it a lot already. We tested it for over a year together with customers, but as usual, they got a really strong NDA from us, and we also obviously gave them a strong NDA to not talk about that prototype machine. But for EMO, we prepared a couple of applications.
Yeah.
And by the way, while Vreni prepares to ask the questions, usually the parts that we have for a fair or something like that, they sit on my desk. I have a small desk here where we gather around, like right now with microphones, but usually I have my small meetings here, and they're sitting on the top of the table. The parts we're going to show at EMO, they're on a heavyweight, how do you call it, carriage or what?
Cart, yeah.
Cart.
Yeah, on like a tool room style cart.
Yeah, sitting here and actually taking quite a bit of my office space here.
Yeah, I mean, they're also not easy to push around because you've got carpet in your office, and that tool cart, I think, is at the moment overloaded. Yeah.
It's bent.
Yeah, a little bit.
So the first part we will show at the EMO, it's the optomechanical housing. We also have it in like smaller. We did it on the HD as well. I don't know, what's the weight of it, Marvin?
Yeah.
You did it, so...
Yeah, so this was the first sample part we started doing on the Fortis. I think more than 2 months ago we started on that one. So basically we showed that part last year at AMB. Because our salespeople have always been asking me for like, Marvin, can you do larger sample parts? We want to really show what the machine can do. And an optomechanical housing is basically an aluminum frame for optical assemblies. If you imagine, if you have an environment which is challenging in terms of, for example, vibrations or accelerations. So for example, launching something into space like a telescope, it's really important that the structure and the precision of the optical assembly comes from like a mechanical part and not from fiddling with small screws and bending or putting foil below one thing, because that wouldn't survive a satellite start. The requirements on these parts is quite large. So for example, on optomechanical housing, typically you have like positional accuracies of 2 microns, you have flatnesses of 1 micron. And this was something the HD excelled at, and we did a part for AMB, which was basically the maximum size the HD felt really comfortable, where you didn't have to do extra evasion moves in CAM to get the tools and everything. And that part was 180 by 180 by 150 millimeters. Now, it's a really cool application for Kern machine, a really cool application for the HD, but there's obviously larger telescopes around. There's also semiconductor housings. And Simon and I discussed this, and we were like, okay, we want a large optomechanical housing. It's kind of funny because we did exactly the same model, we just supersized it. And if you hear, oh, it's now 2.2 times larger, so it's basically 400 by 400 by 320 millimeters, then you're like, oh, it's only 2.2 times. But you have to imagine this is 11.9 times the weight. So the HD part you can easily lift in, it's 13.6 kilograms raw stock. And here it's 180 kilograms of aluminum you have to lift into the machine.
By the way, did we say what the maximum workpiece weight is? Yeah, we said that. 300 kilograms?
Yes.
Yeah.
So it's close.
Yeah. No, seriously, this is a massive chunk of aluminum. I remember when I ordered the aluminum, I came up to Simon and was just like, hey, I just ordered 2 tons of aluminum for sample preparation. And he looked at me like I'm crazy.
I've never ever an invoice or an order came on my desk for raw material.
You're a busy man.
Because of this sheer sum.
Yeah.
It ended up here. I had to approve it.
Yeah. So yeah, the housing is like massively larger. It's roughly 12 times the weight. The finished part is about 65 kilograms, which is also 12 times the weight. And it actually only took us about 6 times as long to mill because the new spindle is so powerful. So roughing really was a breeze. And on the finishing of this, 24,000 RPM is quite a fast spindle. And then we used like 4 flute cutters. And then it really was blazing along at similar speeds to an HD, which is really nice, just like with massive cutters.
I think I have roughly 35 videos of that operation on my mobile phone.
Yeah, I think we also did like one of our, so Simon and I typically have like a one-on-one meeting on Fridays, and we did one of those meetings next to Fortis instead of in your office because I was like, you just have to see it rough, and then we didn't speak about anything but just like watch the machine blasting aluminum around. It was a nice one.
And I think that's a very nice thing also to show, to see acceleration, speed, 60 meters per minute and things like that. This is the same specs we have on micro HD, which is really necessary to get also the performance besides the quality out of that machine. And it's even more important, you see, because of the sheer size of the workpieces, you make a real difference in terms of travel speed, etc., especially in the roughing process.
Yeah, I have to say when I was milling that part, basically the first day was just roughing out the part. And I was super giddy and happy and running around the building and waving like giant enormous insert cutters into people's faces and be like, give me all your money or I'm gonna kill you with this insert cutter. So Marvin was just like on a mad spree through the building. But it was so much fun because it's a big machine. So the insert cutter we used for like roughing the sides, it's a 63 millimeter insert cutter, 5 flute. We did a depth of cut of 5.5 millimeter, width of cut of 45 millimeters, 12 meters per minute feed rate, which translate to roughly a millimeter feet per tooth, which is insane. So this is like real chips, and then you're blasting out nearly 3 liters, that's nearly a gallon, of aluminum per minute, just like blasting it out. So that was super fun. And obviously it was super fun because large machines are fun. And then I started on the finishing, and this was the moment where I was, okay, this machine is going to be successful, because just like with the HD, when you stand in front of that machine, the beauty in the motion for this machine is just like it's out of this world because it's a hydrostatic machine. Just like that minuscule vibration you always have on roller bearings, your eye doesn't register it. Everything is so smooth, so dampening, and so silent, yes. If you take like not an insert cutter but like an end mill, so we took like a DLC end mill, 20 millimeter diameter, 100 millimeter length, also going to those full 35,000 watts of spindle power, and you couldn't hear the cut. the compressed air was louder than the cut, and that's obviously a very nice tool. But it's also a statement to the hydrostatics that just like dampened so much that chatter never became an issue on this machine.
You expect when you see it moving, you expect the sound of the roller bearings and so on. It is nothing.
No, the machine is completely silent, just like an HD when it's moving. That's really nice.
Okay, so thank you for explaining the first part. The second part we will have at the emo from the Kern Fortis HD will be the SICK wafer chuck, which also you did.
Yeah.
Yeah.
So I think ceramics are one of our like focus issues at Kern. I remember very well, Simon, you started the ceramics project in 2019. Tell us a little bit about our motivation about getting into ceramics.
Yeah, so at the beginning, to be fair, so we saw that let's put it like that. So special materials are on the run. So we got more and more requests in special materials like ceramics, etc., and especially also from one customer, where we had a second and a third step from a product that we did at that day. And of course, it would have been very painful to lose this kind of business, but the real challenge was there was no one else there who could do it. So at that time, having you as a great talent in the team, being able to tackle that the challenge, we started investigating, and really very quickly the outcome was, okay, we cannot proceed with, I should say, the standard. The standard processes and standard way, standard tools, standard cutting parameters. So at that time, I think it was a big risk to actually go into that. But I would say, looking back at the 10 years I'm with Kern right now, that was surely one of the, and it wasn't only my decision, but having you there at the right spots and actually doing that was one of the biggest things we've done at that time. And today, when we see how many machines we have milling from zero dual, silicon carbide,
zirconia oxide,
aluminium oxide, whatever, that's just crazy. And this is, it's not like, sorry to talk so much about that, but I'm emotional. Can you feel that? It's walk the talk. So we're talking all about, we're gonna help you out. We're gonna transfer know-how from us to you. We're gonna work with customers. We're gonna join forces and really make things happen. This is the best example ever. Yeah. And we have so many customers who completely change their manufacturing environment through having that capability today. And we continuously moving on, getting better. We have a bloody $1 million
scanning electron microscope. Yes.
Gemini in the meanwhile, because of the fact that it's so important for us. Looking into crystal structure of material, who on earth does that? And we see this so beneficial, brings us forward. And this is what we want to do, is the frontier that's really pushing boundaries, getting better, making things possible. And this is the best example for it.
Yeah. And I have to say, this was Simon's idea. While I did the project, it was his idea, and it's been hugely successful. I would even call it our commercially most successful engineering project in the past half decade, because we just sold so many machines with this technology. Really nice. The wafer chuck is an interesting part because you can actually fit it on an HD, but on the HD it's kind of too large. You can only do it with polar milling, and because semiconductor wafers are getting bigger and bigger, those wafer chucks are also getting bigger. So we decided to do like a full scale. On the HD we only ever did like smaller ones. We decided to do a full scale wafer chuck model. It's more of a tech demonstrator, so it has structures you find in wafer chucks. So it has like deep grooves, it has small pins, it has very smooth surfaces, it has free-form surfaces. All of them are structures you find on like real industry parts, and they are arranged on a single wafer. And the interesting thing here is that with our technology, not only are we very competitive in roughing, so a lot of our customers always ask us for ultrasonic, and we are not a fan because ultrasonic is actually creating a lot of subsurface damages in your part. And it's also, I mean, it's really nice when you're drilling a deep hole in ceramics, but when you're, for example, face milling, the effect is minuscule at best. And one of the developments we are doing, and this is because we have the things to do it, was, for example, for a grinding bit for deep. And so, for example, for the roughing, typically like face grinding with small diameter grinding bits is totally wrecking your grinding bit. And we teamed up together with a German manufacturer, Schott Diamantwerkzeuge, there in northern Germany, took their product and did a couple of really rapid innovation cycles. And the tool now, compared to when we started out, has 5 times the material removal rate and 10 times the tool life in silicon carbide face grinding, which is insane. And they actually named that tool after me, so you can order it. It's not reserved for current customers, and it's the Dr. Marv series at Schott Diamantwerkzeuge. But this shows our innovation potential. We took a tool, choose a partner for that, and then innovated that tool so it perfectly fits to our machine system, and then gives our customers a competitive edge over the rest, because it's actually now much quicker than what you can do with ultrasonic there. But because you're introducing less damages, you can also finish it to a much higher degree. We got the material for those wafer chucks because CSIC is enormously expensive. We got that from also a very nice partner. The company Ceramtech gave us the material to produce the parts. And when I was finishing up the wafer chuck and took it out of the machine, they were visiting the factory and I showed it to them and they started taking pictures and they were like, this is the nicest wafer chuck we have ever seen, and they can't wait to apply that technology to themselves. And I think this really shows the potential of the machine. You have roughing power, which outperforms what is on the market, and at the same time you have that current quality, so you can do flawless surfaces. Because of our special know-how in the ductile cutting regime, subsurface damages are reduced. You have no edge breakouts. And this silicon carbide wafer chuck, and I strongly urge every listener to check it out either at the open house day or at the EMO, it really has a mirror finish straight off the machine. There's no polishing, there's no lapping. It's just like flawless surface quality, 30 nanometers roughness. And that is for such a big machine. I mean, we didn't tell them the final weight. We are guessing it's somewhere around 20 tons. Total weight.
15 tons.
15 tons.
Around that time, between 13 and 50. It changed all the time. So I thought, no, it's not going to be that heavy. It's just 13 tons. And I said, it's going to be 15.8 or something like that. Actually, we still we have quite good moving gear in the meanwhile, but loading is going to be an issue that we haven't solved completely for the EMO, for example. So we'll do it the next couple of weeks. Hey, it's a heavy thing, but it doesn't need any special concrete or whatsoever. Standing in our standard hall next to the Stöckli grinder, which is, I don't know, 50 tons or something like that. So it sounds much, but actually it's kind of forgiving too. So it's not that big. Not that bad.
Okay, then let's go to the last part, which we will show at the EMO. It's going to be the aerospace gear.
Yes.
And I think you did not do it.
No.
It was Christoph Steitmeier. Yeah. Mm-hmm.
So this part is actually really cool. You have to imagine on an aerospace turbine, you kind of want the turbine at the end, so at the exhaust point, to spin as fast as possible. But if you have a single shaft inside that, this means the blisk in the beginning, at the entry of the turbine, would be spinning so quickly that it would tear itself apart. So for better fuel economy, what people are actually doing is putting transmission gearboxes into those turbines so that the blisks in the beginning of the turbine spin slower than at the end. And then you get like a radial compression over it. And the thing is, with gears, your efficiency is, of course, the design question, like tooth ratio, gear ratios, but it's also a question of how smooth is the surface and how tight can your tolerances be. If your tolerance stack up is tighter, it's going to be more efficient. And obviously on a plane that does millions of kilometers over its lifetime, even a small change can do this. The transmission gear we are showing, and Christoph Steitmeier did an amazing job on this. It's milled from steel, and it's an arrow-shaped gear profile. So basically it's 2 rows of teeth which meet in the middle. And this means you cannot grind it, because typically gears are crowned with large grinding discs, but here accessibility is impossible. Now, the only solution you can do on this part is basically to ball mill it. and the specification for the like shape error is super low on this one. I think no current machine on the market could do this precision because it has to be done multi-axis simultaneously. You have to go around it. And it is also part which has a really long runtime. So I think the finishing pass is something like 40-45 hours, which means temperature stability really comes to the forefront. Not only did we achieve an amazing surface finish, we measured it to an RA of 0.08 micrometers, so 80 nanometers finish, which in steel for ball milling is exceptional. And you can really see it's a shiny part. It's no mirror finish because this is not required, but it's a really shiny part. It's flawless, and something I also find super interesting is because of the size, you cannot get away with using just a single tool. No ball and mill on the market can withstand that much milling on such a part. And the thing is, you do not see any transitions at all. I mean, this is a statement to Christoph's skill, but also to the machine, that you can actually stop, take a second tool, and there's no single part on this gear where you can find a transition line. And I think this is really impressive. It's also in the finished state, our heaviest workpiece. I believe it's 160 kilograms right now.
The finished part, yeah.
This is what meant stable here.
Yeah, exactly. He asked me, like, can I put it onto that carriage as well? I was like, yeah, sure, you can put it on the cart. And I expected him, because that cart has like 2 levels, one directly above the wheels and one at 1 meter height. And I expected him to put it on the lower level, but I think he was very proud of it, so he put it on the top level. And I'm just like, oh god.
I'm looking at it all day, yeah. And if the sun comes shining in, it creates a wonderful
Claire.
Can you guys still remember the very first thing we did on at that time Albatross or Fortis HD?
The world record milling of steel?
Yeah, exactly. I think we didn't mention that before, did we?
No, we didn't.
Okay, tell us, what did we do?
Okay, so there is a video from another machine tool company where they do the world record in steel material removal rate. Now, obviously, you could just choose a larger spindle. So there's a Swedish company who produces a machine which I think has 0.5 megawatt of spindle power. It wasn't on such of these machines. It was just like standard interface, HSK63. They took a really nice tool from a partner and they did more than 1,000 cubic centimeters per minute material removal rate. And I think one of our developers saw that video and he told us like, hey, we should just like see whether we can beat this record. And we have video footage of that. I took high-speed video footage of it, which we're going to show after EMO or maybe during EMO. And we actually managed it. And I think this is exceptional because this is, I mean, yes, it's a huge machine. It's heavy. It is powerful from the spindle. But after all, it's a machine with which you can still split the micron. It's a precision machine. It's a Kern. But we actually managed to outperform the world record in material removal.
That's more or less the first thing, at least that I saw that happened on the machine. I think it wasn't the first chip we've ever done, but that was more or less the first thing we said, okay, come, we're going to run the Fortis. Do you want to see it? And that was the first thing actually I saw the machine doing is beating the world record. So you don't say beating, what was the word you're using? So I think we did exactly the world record. Not more, because I said we don't want to overdo it and stay humble at the beginning.
I think we went like 5% over it.
Yeah, something like that, yeah.
Yeah, and I have to say, I sometimes mill on Hermler machines, which are lovely machines. I'm a huge fan. But this thing, in terms of material removal, especially in steel, outperforms everything. It's unbelievable. This is one beast of a machine, I have to say. Really nice one. We actually still have the chips and also video of the first thing we ever milled on that machine. You have that video on your phone as well.
Yes.
And I think this also shows a little bit of our madness. Instead of like taking a small end mill and milling a tiny pocket, we took a huge chunk of aluminum and a large insert cutter and just like went after it. Yeah, that's really nice. Okay. Thanks for your time. I think this wraps up our episode fantastically. We are long overdue in our meeting, and we also made a massively long episode. Thank you very much. Simon, Verena, and I will be at EMO. Come up, chat with us. The lead developer of the Fortis Christian Meyer, with whom we did the last episode, will also be there. Come up, take selfies with the machine, look at it, talk to us. I think everybody's super motivated.
Feel the magic, feel the emotions.
Okay,
come
yes.
up, everybody's welcome as always. So we want to share our secrets and give a deeper view into the machine and talk technical stuff and get your challenges.
We are in Hall 12. Do you know this booth number, Verena? Yeah, exactly. Okay, we are in Hall 12 and none of us know the booth number, but you can't miss us. We have a huge booth.
We're directly next to rovers. We're front facing a rover. We are next to as you always say, be close to your friends, be closer to your enemies. No, we don't have enemies, but we are exactly where we say our competition is. So we'll see, and hopefully rock the floor with the things we do and we show.
Okay.
Yeah. Thank you very much, Marvin.
Yeah,
Goodbye.
looking forward to seeing you all. Goodbye and thank you.
Bye-bye.